On the banks of Pakistan's mighty Indus River stands an engineering colossus, the Tarbela Dam. Costing around $3 billion, it is hailed as the largest earth-filled dam in the world. In today's video, we'll explore its fascinating origins, the massive socio-economic and environmental impacts, the incredible science behind earth-filled dams, and the state-of-the-art turbines that turn rushing river water into electrical power for millions of people. Back in the 1960s, when newly independent Pakistan faced the monumental task of regulating the flow of the Indus River, a lifeline for the country's agriculture, severe seasonal fluctuations meant that farmers sometimes experienced devastating floods in the monsoon season and crippling drought in drier months. The solution arrived in the form of the Indus Basin Project, part of which was the construction of the Tarbela Dam. Backed by funding from the World Bank and other international donors, construction began in 1968. Originally expected to cost around $1.5 billion, technical challenges, design modifications, and inflation caused that figure to nearly double. By the time Tarbela Dam began operations in the mid-1970s, total expenditures reached the $3 billion mark, making it one of the most expensive engineering projects in South Asia at that time. Megaprojects around the world always come with socio- and economic impacts. Let's take a look at the impacts Tarbela Dam has had. Large-scale infrastructure often means large-scale displacement. Over 100 villages were submerged when Tarbela's vast reservoir filled, affecting upwards of 80,000 people. Compensation packages included monetary payments and relocation to new settlements. Yet for many, the emotional and economic toll was immense. Families lost ancestral farmland and tight-knit communities were uprooted. On the flip side, the dam transformed Pakistan's agricultural landscape. By storing massive quantities of water, Tarbela ensured a more consistent supply for irrigating millions of hectares of farmland, boosting crop yields and providing a more reliable source of livelihood for countless farmers downstream. Still, the debate over whether these benefits outweighed the human cost continues to this day. Be sure to leave a comment if you think the sacrifice was worth the upside. Also, if you are enjoying this, give us a thumbs up and subscribe to Engineeringness for more explorations into mega projects located around the world. Tarbela's signature feature is that it's an earth-filled or embankment dam, the largest of its kind in the world. But how exactly is it different from other dam types such as concrete gravity, arch dams, or buttress dams? 1. Construction materials. While concrete gravity dams, like the Hoover Dam in the US, rely on an enormous block of concrete to resist water pressure, earth-filled dams primarily use compacted soil and rock. These materials form a broad embankment that is both strong and flexible. Arch dams use a curved concrete structure to direct water pressure into the valley walls. The Hoover Dam's arch wall undergoes deformation under the water load, which results in compression, reducing the length of both sides of the wall. This load leads to a strengthening of the wall to aiding its resistance to the huge pressures exerted by the water. Earth-filled dams distribute the load across layers of materials that include a compacted impervious core, often clay, flanked by layers of gravel and rock to filter and drain seepage. 2. Load distribution and flexibility. An earth-filled dam can settle and adjust to shifts in the foundation over time. This adaptability is crucial in regions with softer ground or significant seismic activity, which can be a regular occurrence for Pakistan due to its location on several major fault lines. Unlike concrete dams, being rigid structures, they can suffer serious damage if the ground beneath them shifts to a great enough extent. 3. Local material. Earth-filled dams frequently rely on nearby materials such as soil and rock excavated from the surrounding area. This can be more economical for wide valleys like Tarbela's, whereas concrete or steel might be expensive or difficult to transport in remote regions. 4. Dam dimensions. Tarbela Dam stands about 148 meters high or 485 feet and spans roughly 2,743 meters or 9,000 feet across its crest. Beneath this embankment are carefully engineered zones, an impervious clay core to stop water seepage, transition layers to protect the core, and outer shells of rock for stability. In building Tarbela Dam, the engineers contended with complex geotechnical conditions. Precisely layering and compacting the enormous volume of earthen materials was an incredible challenge. Any compromise in the impervious core could lead to internal erosion or piping, which is a serious hazard for embankment dams. Piping in earthen dams, also known as internal erosion, occurs when seepage water carries soil particles away, creating a channel or pipe that can lead to dam failure. This process starts at the downstream side and progresses towards the reservoir, potentially causing a catastrophic breach. Sedimentation posed another long-term issue. The Indus River carries vast amounts of silt which can accumulate in the reservoir and reduce water storage capacity. Over time, this can diminish irrigation potential and lower hydroelectric output. Engineers have attempted mitigation strategies like flushing sluices to clear out deposited sediment, but managing silt remains an ongoing battle. So, how does Tarbela Dam generate electricity? Beyond water regulation and irrigation, Tarbela Dam plays a crucial role in powering Pakistan. At the heart of this operation lies a set of Francis turbines, one of the most widely used turbines in large-scale hydroelectric plants. How do these work? 1. Water intake and penstocks. Water from Tarbela's reservoir enters intake structures at the dam. From there, it's channeled down penstocks, massive pipes designed to guide high-pressure flow straight into the power station below. 2. Francis turbine mechanics. As the water rushes through the penstocks, it strikes curved blades mounted on a runner. Francis turbines are mixed-flow turbines, meaning water enters radially from the side and exits axially through the center. The shape of the blades transforms the water's kinetic energy into rotational energy, spinning the runner at high speed. 3. Conversion to electrical energy. A shaft connects each turbine to a generator rotor. As the rotor spins inside the generator's stator, the magnetic field induces an electric current in the surrounding coils. Initially produced at relatively low voltage, the electricity is quickly stepped up by transformers for long-distance transmission. 4. Capacity and upgrades. With multiple turbine generator units, Tarbela's installed capacity now exceeds 4,800 megawatts, ranking it among the largest hydroelectric installations in the region. Recent extension projects aim to further boost this capacity, potentially inching closer to or surpassing 6,000 megawatts in the near future. Tarbela Dam stands not only as a massive earth-filled embankment on the Indus River, but also as a symbol of ambition, innovation, and the delicate balance between progress and preservation. From its monumental cost, over $3 billion, to the displacement of thousands, the lessons learned at Tarbela echo across countless engineering projects worldwide. Yet, for all its controversies, Tarbela Dam has transformed Pakistan's agricultural sector and provides a vital chunk of the country's electricity, testament to the power of harnessing nature for human needs, while also highlighting the complexities and responsibilities that come with such power. Thank you for watching this episode of Engineeringness. What other engineering marvels or controversies would you like us to explore? Let us know below. Until next time, stay curious and keep celebrating human ingenuity.